Hello everyone, welcome to the second video of week 2. In this video we introduce a couple of concepts that assess the performance of an estimator. Let us return to the serial numbers example. Here, the estimation problem could be simplified by drawing numbered balls from an urn. We have seen two methods to estimate the total numbers of balls in the urn. Method 1, the doubled average, minus 1, and method 2, the inflated maximum, minus 1. By means of a simulation experiment, we mimic the drawing of the balls. And from this, we learned how the uncertainty when drawing the balls transfers into uncertainty about the value of the estimators. Different samples resulted in different values for the estimators. So this illustrates that we cannot expect from an estimation procedure to always find the correct value for the parameter. The best thing that we can hope for is that possible outcomes of the estimator vary around the unknown true value of the parameter of interest. Now, in our simulation, we chose the number of balls in the urn to be 1000, and in each iteration we drew 10 balls without replacement. And both estimation methods then produced values varying around 1000. The variation for estimator 2 turned out to be smaller than for estimator 1, and from this we concluded that estimator 2 is the better one. Now, will this also be the case if we have a different number of balls in the urn or if we draw a different number of balls from the urn? Now, to answer this question, we will turn the observed behavior of the estimation procedures into a rigorous mathematical concept. Similar to video 5 in week 1, the uncertainty in drawing balls is modeled by considering the observations little x1 to little xn as realizations of random variables capital X1 up to capital Xn. Estimate T1 is the following combination of the observations. Now, to model the remaining uncertainty in the estimate, we consider the value little t1 as the realization of a random variable capital T1. This is the random variable formed by the same combination, but now built from the random variables capital X1 to capital Xn that we use to model the observations. In the same way, estimate little t2 is modeled as the realization of the random variable capital T2. This is the random variable formed by another combination, but of the same random variables x1 up to xn. Now, to emphasize the difference between the random variables capital T1 and capital T2 and their realizations little t1 and little t2, we call the random variables capital T1 and capital T2 estimators. And we call the observed values little t1 and little t2 estimates. This brings us to the following formal definition. Suppose we have a data set little x1 up to little xn that we model as realizations of random variables capital X1 up to capital Xn. Any t, which is some function of the data set, is called an estimate. The corresponding random variable capital T, which is the same function of the random variables x1 to xn, is called an estimator. So an estimator, capital T, is a random variable. And this means it has a probability distribution. This distribution describes the uncertainty in the estimation method and is called the sampling distribution of T. Now, we will use this distribution to define a mathematical concept that assesses the performance of T. Now, to get an idea how to do that, consider estimator T1 in our serial number example. The parameter of interest is K, the number of balls in the urn. Now, in the simulation, this was chosen to be 1000. We simulated 10,000 realizations of T1, which turned out to vary around 1000. And the amount of variation assesses the performance of T1. Now, the distance between each realization little t and 1000 can be quantified by the squared error. And the total variation of capital T can then be quantified by the average of all squared errors with respect to 1000. Now, for any other number of balls k in the urn, the amount of variation can then be quantified by the average of all squared errors with respect to k. And according to the law of large numbers, this average is roughly equal to the expectation of the random variable t1 minus k squared. Now, this quantity is called the mean squared error of t1 with respect to k. Note that for any k and n, this is a general formula that remains the same. And in this way, we have developed a measure of performance for an estimator t1 that works for all possibilities for k and n. Now, this brings us to the following general definition. Suppose that t is an estimator built from random variables x1 up to xn, whose distribution depends on some parameter theta. Then the mean squared error, or MSE, for t with respect to theta is defined as the expectation of t minus theta squared. Now, since t is built from xi's whose distribution depends on theta, the sampling distribution of t will also depend on theta. And in particular, its expectations will depend on theta. Now, to emphasize this, we sometimes put a subscript theta below the expectation. Now, the mean squared error can be decomposed in two parts, and this can be seen as follows. From probability theory, we can use the rule for the variance of a random variable z to get the following expression for the second moment. When we take z equal to t minus theta, we can write the mean squared error as the sum of the variance of t minus theta plus the squared expectation of t minus theta. Now, for simplicity, we leave out the subscripts theta from the expectation and variance. Now, in the formula, theta is unknown, but it is a non-random constant. And that means that the variance of t minus theta is equal to the variance of just t. And for the second term, we can use the linearity of expectations and write this as the squared difference between the expectation of t and theta. Summarizing, we can decompose the mean squared error of t as follows. And here we use the subscript theta again to emphasize that the variance and expectation of t depend on theta. The variance of t measures the amount of variation of the estimator around its expectation. And the second term measures how much on average the estimator deviates from theta. Now, before continuing with the mean squared error, let us first concentrate on the second term. The difference between the expectation of t and theta is called the bias. Now, because the distribution of t depends on theta, the expectation of t will be some function of theta. And this is emphasized by the subscript theta. The difference between this expectation and theta itself is called the bias of t with respect to theta. When the bias is positive, we have the following situation. In this case, the estimator t systematically produces values that are larger than theta. And when the bias is negative, then the estimator systematically produces values that are smaller than theta. Only when the bias is zero, then the realizations of t are on average equal to theta. This brings us to the next definition. Suppose that the sampling distribution of an estimator t depends on some unknown parameter theta. Now, this means that the expectation of t will also depend on theta. When this expectation is equal to theta itself, for any possible value of the parameter theta, then we call t an unbiased estimator for theta. As an example, consider random variables x1 up to xn, and suppose that each xi has the same expectation mu, and consider the sample mean as an estimator for mu. Is this an unbiased estimator for mu? Well, in order to check this, we have to compute the expectation of x bar. Using linearity of expectations, this is equal to the average of the individual expectations. And since each individual expectation is equal to mu, we find that the expectation of x bar is equal to mu. Now, this argument holds for any value of mu, so the sample mean is an unbiased estimator for mu. Now let us return to the serial numbers example. The estimation problem was simplified to drawing balls without replacement from an urn with k balls. Now let x1 denote the first number drawn from the urn, x2 the number on the second ball, up to xn denoting the number of the last ball drawn from the urn. Since we drew without replacement, the random variables are dependent. Nevertheless, they all have the same marginal probability distribution. Each xi has possible values 1 up to k with equal probability 1 over k. Now this may come as a surprise, but this can be shown with elementary probability theory, and you are invited to check this for yourself in one of the exercises. Now the expectation of xi is the sum over all possible values times their corresponding probability. And this can be simplified to this expression. As we argued in video 1 of this week, this further simplifies to k plus 1 over 2. So, we are dealing with random variables x1 up to xn that have the same expectation. And we just learned that in such a case, the sample mean is an unbiased estimator for this expectation. Now this means that the expectation of x bar is equal to k plus 1 over 2. And a direct consequence is that estimator 1 in the serial number example is an unbiased estimator for k. Indeed, linearity of expectation yields that T1 has expectation k. Now the situation for estimator 2 is more complicated. And it turns out that the expectation of the maximum is equal to the expression on the right-hand side. It goes too far to show this here, but the consequence is that estimator 2 is also an unbiased estimator for k. Again, linearity of expectation yields that T2 also has expectation k. Now this explains why both estimators in the simulation are on average almost equal to 1000. Now the mathematical property that they are both unbiased guarantees that this will always be the case, no matter how many balls there are in the urn and no matter how much balls we draw from the urn. This brings us to the end of video 2 of this week. In the next video, we continue with the concept of mean squared error and discuss some properties of unbiased estimators. See you then.